11.1 Space Figures and Cross Sections. The objective in this lesson is to recognize polyhedra and their parts and to visualize cross sections of these space figures. So let's start off with some vocabulary. A polyhedron is a space figure, which means that it is a three-dimensional figure whose surfaces are polygons. So if we look over here at our figure, we can see that it's a three-dimensional figure and it is made up of quadrilaterals, which are polygons. Polyhedron is a three-dimensional figure. Polygons are two-dimensional figures. All right, each face of the figure is a polygon. So our flat surfaces here are called faces. An edge is a segment that is formed by the intersection of two faces. So if we look here, these are the edges. You can see where our faces come together. They come together in an edge. You remember way back, where two planes intersect is a line. Our two planes are intersecting a line. We call that an edge. And a vertex is a point where three or more edges intersect. And we know what vertices are in our polyhedrons here. This is where our edges of our faces are intersecting. And a dashed line indicates that an edge is hidden from view. And we have seen this before. This just means that it's behind the figure. Sometimes it just makes it a little easier to see. So let's take this information and start with our first problem here. We want to know how many vertices, edges, and faces are in our polyhedron. And starting with the vertices is usually pretty like the easiest way to start. And a hint here is to pick a point and then work your way around. So we're going to go 1, 2, 3, 4 on this section, and then we have one more up here at the top. So that gives us 5 vertices. Vertices are points, so they are named as points. Okay, edges. Again, the best way to count an edge is to go around the top, then go around the middle and go around the bottom, or vice versa, work your way up from the bottom. But you need to pick an edge and then work your way around. So we have 1, 2, 3, 4 around the bottom. And now we're going to go around the middle here. 1, 2, 3, 4 around the middle. So that's going to give us 8 edges. Those are segments, so they are named as segments. And then faces. We have one face here on the bottom, and then as we go around the middle, there's 4 triangles there in the middle, so that gives us a total of 5 faces. And they are polygons, so when we name them, you can see we have 4 triangles and a quadrilateral there on the bottom. So that means it's your turn. Go ahead and pause the video and do the next problem. The first problem asked us how many vertices, edges, and faces are in our polyhedron. And so vertices, I found 6 of them. I started on the left side over here and just counted 1, 2, 3, 4 on the back, and then 1, 2 over here on the right side. Give me 6. The edges, I did the same thing. I'm going to start on this left side over here and go 1, 2, 3, 4. And then on the front, I've already counted the one on the left, so it's just 1, 2 there. On the back, it's the same thing, 2 there. And then one more on the front. That gives us 9. And then faces, we have 1 in the back there, 1 on the left side, I guess that is. Back, front, and then the bottom, and then this top. So that gives us 5 faces. Now the next question says, is segment TV an edge? Well, here is point T, here is point V, and we can connect them to form a segment, but that is not an edge because an edge is defined as the intersection of two faces. So these are not bad, but you have to keep track of where you're at and be careful when you're counting. Don't recount pieces that you've already counted. It's the hardest part of this. Sometimes shading a piece in will help it stand out. You know, geometry is easier in color. All right, next. Leonhard Euler was a Swiss mathematician. He's very famous in math circles. He did a lot of things, but what we are interested in is Euler's formula. And it develops a relationship among the number of faces, vertices, and edges of our polyhedron. And so what Euler's formula says is that the sum of the number of faces and vertices equals 2 more than the number of edges. And so we get this formula right here. Faces plus vertices equals edges plus 2. So let's do a problem with that formula. Our problem here says how many faces and vertices and edges does the polyhedron have, and verify Euler's formula. So I like to start with the vertices. So I'm going to go around the top. 1, 2, 3, 4, 5, 6. I pick a point, worked my way around. Do the same on the bottom. 3, 4, 5, 6 more down there. So we get 12 vertices. And then I like to do edges next. And I'm just going to start on the top, work my way around. 1, 2, 3, 4, 5, 6 there. And now I'm going to go around the middle. 1, 2, 3, 4, and there's 5 and 6 in the back. And then go around the bottom. 1, 2, 3, 4, 5, 6 more around the bottom. So that gives us 18. Now that should not be a surprise because we have 6 vertices. So all of those are going to be connected top to bottom. And last here is our faces. Well, we have 1 on the top, 1 on the bottom, and then 1, 2, 3, 4, 5, 6 around the middle. So that's 6 more around the middle. So that gives us 8. And again, this should not be a surprise because our top and bottom have 6 edges, which have to be connected to each other. So no surprise here. We write Euler's formula, faces plus vertices equals edges plus 2. So 8 plus 12 equals 18 plus 2, 20 equals 20, and check. Verified Euler's formula. That means that it's your turn. Pause the video, do the next 2 problems. We were asked to use Euler's formula to find the missing numbers. We were given edges and vertices. I wrote my formula, substitute in, did my math, and I found 12 faces. Now, when I look at the figure, if we can assume that we can see about half of the figure, we can count 6 faces, so 12 faces seems reasonable. On the next one, we were given faces and vertices, so we needed to find edges. Just formula, substitute in, solve. Got 30 edges. And again, if we assume that we can see about half of the figure, I counted up and I came up with about 15 edges that are visible, maybe 16. But still, that seems like 30 would be a reasonable number of edges. So Euler's formula is pretty cool. Moving on. In 2 dimensions, that means we're using a net, Euler's formula changes. So if we're counting faces and vertices and edges on a net, we use faces plus vertices equals edges plus 1. Now the reason for this is when we unfold our figure, some of our vertices and edges are going to get counted multiple times. So let's take a look at how this works here. First thing I like to do on this one is easiest to count faces first. So we have 1, 2, 3, 4, 5, 6 faces. and then one up here, and one down here. So we have 8 faces. Now, we just figured that out on a previous problem. We just unfolded, and we ended up with the 6 rectangles from the middle and a hexagon on the top and bottom. So of course we're going to have 8 faces. Now the number of vertices, this gets to be a little more difficult to count. So you have to be careful here, and I'm going to start in the middle, and I count 1, 2, 3, 4, 5, 6, 7 across the top there, and I know that I'm going to have the same number, right, across the bottom of that. And now I'm going to count around the top, but be careful because these 2 right here have already been counted. So 1, 2, 3, there's 4 more there, and the same on the bottom here, 4 more there. So total together, that gives us 22 vertices. Now the edges takes even a little bit more to count. So I am just going to go start in the middle again and go across this section. 1, 2, 3, 4, 5. There's 6 across the top. That means there's also going to be 6 across the bottom here. Now let's go to the vertical ones. 1, 2, 3, 4, 5, 6, 7 this time. That's because when we fold it back up, the beginning and end here are the same edge. So when it's unfolded, I told you we count some of these things multiple times. Then I'm going to go to a top. Now don't forget we've already counted this one, so there's 1, 2, 3, 4, 5. And the same on the bottom, 1, 2, 3, 4, 5, because we've already counted this one. And if we add all that up, we get 29 edges. So we write our formula. Don't forget this time it's a net, so we are doing E plus 1. Substitute in, and 30 equals 30. Now it's your turn. Go ahead and do the next problem. These problems had us counting faces, vertices, and edges in 3 dimensions and in 2 dimensions using a net. The first one was for the solid, and so the faces, there's 1 on top, there's 1, 2, 3, 4 around the middle, 1 on the bottom, that gave us 6. Vertices, again, I started on the top, just worked my way around. There's 4 there. Around the bottom, there's 4 more there. That gave us 8. And edges, again, I'm going to start around the top. 1, 2, 3, 4 around the top. Now I'm going to go around the middle. 1, 2, 3, 4 around the middle, and then around the bottom. Just work my way around. 4 more, that gives me 12. Write Euler's formula, substitute in, and 14 equals 14. So we did good. On the next problem, it said draw a net. So I just used the bottom. I just took this bottom piece here and flattened it out, folded down my sides, and then stuck the top up on the top. I could have put it on I could put it left, right, bottom. Doesn't matter. You could unfold it any way you like. I just find this to be the easiest. Now this is a little more difficult to count. Our faces, that's easy. 1, 2, 3, 4, 5, 6. Of course there is, because that's what we had last time. Now vertices, the way I did the vertices was I kind of went across in rows. So there's 2 here, and then I went to the next row, 2 here, and then 1, 2, 3, 4, and then this one also has 4, and then 2 more here, and so that made 14. Now the edges, I kind of did the same thing. So across top here there's 1, and then I've got vertical ones here 2, and then 1 more there, and then 2 there. Now I'm going across the horizontal 1, 2, 3, and then vertical 1, 2, 3, 4. 3 more here, 2 more here, 1 more down here. Add them all up, turns into 19. Plug it into the 2-dimensional Euler's formula, and we get 20 equals 20. All you have to do is be careful when you're counting. Color is your friend. Moving on, to cross sections. A little vocabulary. Cross section is the intersection of a solid and a plane. So if you think of this like a loaf of bread, a loaf of bread is our solid. It's three-dimensional, and let's call our loaf of bread a square. And so we're looking at it from the end, and it's a square, and it has these rectangles that go down, to make the sides and the top and the bottom, and then it's a square on the other end. When you slice that loaf of bread, a slice of bread has the same shape as your front and back. And so that's what we're doing here. You can think of this as a very thin slice of your solid. So let's look at our example here. We have a Toblerone. I like to relate these to food because they seem so much easier when you do that. And this is a triangle. It's got rectangles that go down the length. So we've got our Toblerone here. And if we slice through it like a loaf of bread, what shape do we end up with? Well, if we slice it, we're just kind of cutting it in half, and our front and back are triangles. So the slice we cut out of it is going to be a triangle as well. Now, slicing a loaf of bread or a Toblerone like this is pretty easy. That's easy to see. Now, what happens when we take a less normal figure and slice it in a less normal direction? Well, our cylinder here, this is like a soup can or a soda can or something like that. The best way to look at these is, where does the plane cut across? So I am just going to draw in. I know it cuts across the top and bottom there. And then it's going to cut my sides right there. So what shape do we end up with? We end up with a rectangle. And it's going to be the same on this figure over here. Let's draw in the rest of our, dash in the rest of our circle here so it's a little easier to see. And when our plane, where does our plane cut? Well, it cuts halfway across this circle, cuts halfway across this circle, and then those connect there. You can see that figure that I drew is in the plane, and that's a rectangle. These can be a little challenging, but I believe that you can do it. So why don't you give it a try on the next problem? Go ahead. How'd you do on these? All right, it says for the solid, describe the cross-section that's formed by each of the following. So a horizontal plane. So that means I'm cutting across the figure in this direction. So what happens if I slice it this way? Well, what figure am I slicing? I'm just slicing a circle. There's a circle on top, there's a circle on the bottom. I'm just cutting it in half, and there's still going to be a circle, granted medium-sized. Top is large, bottom is small, so a medium-sized circle. Now what happens when our plane goes vertical? Well, let's think of it this way. We're cutting a plane like this. So it's going to slice through here. It's going to slice through here. And when I cut the front off of this, what's going to be left is a trapezoid. That's like getting the rectangle out of the cylinder. We get a trapezoid out of this. Now, there are some hints on how to make this work. Let's look at this, the bottom here. We are going to use one of our postulates from the very, very beginning. The intersection of two planes is exactly one line. So let's look at how this works. If we have, because we're cutting our solid with a plane, right? We're putting a plane through this solid figure. So we have a cube here, and we want to know what is the shape of the cross section. So if we, cut through it, this one's going to be easy because if we cut horizontal or we cut vertical, it's just another square. But what if we cut like the corner off of it? So I like to think of this like maybe as a block of cheese. And if we're cutting the corner off, I'm going to look at it and say, well, I'm going to slice down here and slice down here. If you draw your parallel segments, right, we're doing a vertical segment here, vertical plane, and then I just connect the two back there. And what we end up with is just a rectangle. And what this is going to look like is we have our block of cheese here, and what we're going to end up with is just this little piece cut off of the corner. And you can visualize that. So I like to incorporate these into like things I know. Food is really easy. You've cut food before, so think about what happens when you slice off a corner of a block of cheese or you slice bread. Okay, that's going to make them easier. Now we'll do this last problem here together. What is the cross section formed by a horizontal plane? So if we have our cube and we cut it horizontally, well, how can we, what does horizontal mean? It means cross this way. So we're cutting a plane like that. So I'm going to dash in my lines back here. I'm going to draw a horizontal line in front and a horizontal line in back, and then I'm just going to connect them. So you can see that our horizontal plane cut through it that way, and this makes perfect sense. It's just going to be a square that we cut off. These problems require some thinking. When you're counting faces, edges, and vertices, use your colors to help you. Find a spot to start, work your way around. When you are doing cross sections, again, use your colors. Think about what a vertical or horizontal plane would look like and try to relate them to something you know. Work carefully on these, and I am sure you will do very well. Enjoy your homework, and don't forget to do your video quiz.